A paralyzed Noland with an implanted Neuralink can already outperform a human in speed in this game where you have to click a randomly appearing blue target on a grid in 1 minute. Kind of like AimLab. Beating you right now, he probably can't, especially if you play Deadlock or Apex, but someone around 40 years old, most likely. And in the future, this metric will grow so much that even the best esports players will have a hard time competing with him. He controls the cursor literally with the power of thought. On his streams, he sits and plays Civilization or Mario Kart, also just by thinking about it. Today, I'll explain how this works. Mind-controlled input, how the chip is implanted into the brain, the safety of all this, and a bunch of other interesting things. To understand how mind control works, we'll quickly cover two things, the brain and the chip itself. First, I'll show you a video from Elon Musk's presentation, and then I'll explain it in simpler words so it sticks.
You want to move your cursor. Like all information you can perceive or imagine, the intent to move a computer cursor is represented in your brain. Your brain is composed of nearly 100 billion cells called neurons. Neurons come in many complex shapes, but generally they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon-dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron. Information about everything from movement, to vision, to hearing, to hunger, to dreaming during sleep, everything you can experience can be found by recording these electrical signals in different areas of the brain. Information about moving your cursor can be found in a number of brain areas, including the primary motor cortex, or M1. When the cursor is moved up, some neurons in M1 will fire a lot, some will fire a little, and others will be silent, and vice versa if the cursor is moved down. In other brain areas, relevant information is represented in more complex ways, which can be learned with more sophisticated models. Through these relationships, we can begin to decode the communication signals in the brain. And by recording enough neurons, movement intent can be elucidated with higher fidelity.
Basically and simply put, the brain is a big computer with about 100 billion neurons that communicate with each other. Imagine that I am a neuron and I don't have two arms, but many. The arms are dendrites, and the leg is an axon, and the ball is information. A neuron has lots of dendrites, so imagine I have many hands. They can only catch balls, information, they can't throw, only catch, and the leg is the axon, the channel through which the neuron sends info, and the people, neurons around me, are the same. Lots of hands, but one leg they use to kick this info, and so I, the neuron, have caught a bunch of balls, information, but I can give them to another neuron only by kicking with the leg, and when I kick, an action potential occurs, which is what the Neuralink chip records. An action potential is an electrical signal. Yes, we have electricity in the brain, and it's exactly this electrical signal that the chip scans. And the chip that's implanted into the brain looks like this, roughly the size of a coin. It consists of a case, a charging coil, a battery. The chip charges wirelessly like an Apple Watch. That's why the coil is needed. That's how wireless chargers work. Coils in your phone and watch pass current to batteries, then all the electronics for processing signals and these little wires. They're extremely thin, 4 microns, 25 times thinner than your hair. The tip of each thread that goes into the brain is an electrode, which records signals when a neuron kicks the ball to another. When it catches, only when it kicks, because only then can the electrical current be recorded. And now you'll quickly understand how it's all controlled by thought. There's a chip placed into the skull, I'll show later how, And the threads are inserted into the brain so they can detect these electrical signals because that's how the brain communicates. And when you want to move your hand, that doesn't happen in some random place in the brain, but in specific areas. That's where the threads are placed, and the threads pick up that signal that you want to move your hand left or right, and the cursor moves accordingly. This is not eye tracking. This is literally, in the most direct sense, mind control. And Noland, who was the first to get the chip, is paralyzed, but interestingly, the thought of moving your hand right triggers the same neurons as actually moving your hand right. Before implantation, they do an MRI and ask him to imagine moving his hand right. They see which region lights up and mark it, then left, and so on, and then based on this data and where the brain activated, they implant the threads there. And now Nolan just thinks about moving his hand to the right, even though he's paralyzed, and the cursor goes there, or up or down. They also mapped left and right mouse clicks. See, it's all like using a mouse. Except the mouse is unnecessary. The mouse is just a middleman. Actually, our hands are also middlemen. Try thinking broader, and you'll realize that the two endpoints in interacting with a computer or phone are us and the device. And when we want to communicate or interact with the phone, we use middlemen, our hands, or even a second middleman, a keyboard or touch screen. These are not the fastest intermediaries, just two limbs that can't keep up with your thoughts. That's why generating a question in your mind takes a second, but typing it takes much longer. Not very efficient. That's why people send voice messages, because typing out what happened to you takes longer than saying it. But here's what's interesting. Our lips and tongue are also slower than our thoughts. We're limited by articulation. Someone might say, I sometimes think slower than I talk. Yes, but words and speech are also intermediaries. Simple example, a picture. It's obviously faster to show it than to describe it. Just like it's faster to think about what you want to search than to type it into Google. Same with moving a cursor. Thinking move right and click is almost instant, whereas thinking hand moves mouse, finger clicks, all that already existed in your brain. The hand and mouse don't speed it up compared to Neuralink. And if someone wants to ask, but I play WebGrid faster than paralyzed Noland, first, I said he's not faster than everyone, only some, and second, this is just the beginning. Neuralink's team noticed something interesting. Noland could move the cursor without thinking about moving his hand. He literally just thought about the cursor moving, and it worked. So we've understood how Neuralink works, how signal transmission happens, and even a bit of how the brain works. Now the most interesting part begins, because in the future, humanity will likely see three amazing things connected with such chips. First, cyber implants, like in Cyberpunk. Progress doesn't stop. We're already living in the most amazing time. AI, Tesla that can already drive itself, Neuralink, SpaceX. Many don't even realize in what era of civilization we're living. And speaking of cyber implants, they're not just possible, they're inevitable. By advancing Neuralink, signals from the brain about what you want to do with your hand can be sent not to a PC, but to that hand. Not for typing text, we already know that's slower, but for tasks where hands matter. And these may not be ordinary hands, but augmented, modified ones, which you can control with the chip. Right now, prosthetics mostly use sensors on their inner surface to detect signals. They work differently than Neuralink and are much, much worse. Second, restoring vision, treating paralysis and certain other conditions. Paralysis is basically nerve damage. The brain sends the signal, but the damaged nerves, a kind of bridge between muscles and brain, don't deliver it. Neuralink often says that physically nothing prevents curing paralysis. No barrier says it's impossible. You can bypass the damaged bridge and send brain signals directly to muscles. How to do this if nerves are damaged? None of us works at Neuralink, but logically, electrodes could be placed near the muscles, making them respond as if from nerves, just bypassing them. The chip, like Neuralink, would read signals and send them to the muscles. A team of very smart people will have to work this out, but I'm sure it will happen fairly soon. Another amazing possibility with the chip is restoring or even enhancing vision, because eyes are also an input device, a middleman, and the important part is the visual cortex, where signals can be sent by stimulating it. Back in 2020, which already feels long ago given tech development speed, there was a study where a monkey with an implant could recognize simple shapes, movement, and letters. This year, Neuralink announced a chip that will help restore vision called blindsight, and the FDA calls it a breakthrough, which it really is, because stimulating the brain can eventually make vision better than human. Just like with a normal arm and a cyber arm, you could upgrade your eyes, gain infrared vision, or zoom in on things, because the eye is also an intermediary between the brain's visual cortex and what we want to see.
But the most interesting and least studied thing is mind-to-mind communication and direct data upload into the brain using such chips. When you won't need to learn a language, you'll just upload it.
I'll write about this in my Telegram channel. It'll be in the description, and I'll be very happy if you join it. I'm doing it to bring viewers there too. It won't have a precise how to do it, but there will be an interesting post. I've heard many very smart people, including Musk, say this is possible. And that monkey with the implant, they were already able to send data into its brain. Anyway, check my Telegram. I'll post a few more interesting things about chips. At the beginning of the video, I also said I'd talk about safety, how the chip is implanted, etc. So let's cover that quickly, because who needs safety when you'll get eagle vision? First, how it's implanted. Neuralink has a robot for this. It's their signature thing because a human can't do this. Humans only oversee the robot as it implants the chip. It's safer than if a human did it, like with laser eye surgery. That's why it's done by a robot. You wouldn't want someone holding a laser in their hands doing your eye correction. That's less precise. Same here, because the human brain is mobile. That's why it's shown as jiggly in games. More mobile than in sheep or monkeys. And the robot can handle this. Plus, there are lots of blood vessels it easily avoids. When they implanted the chip, there wasn't a single drop of blood. That's how precise it is even now, and it'll get even better. The procedure is so fast that the patient can be discharged in 4 to 6 hours. They don't use general anesthesia, and the implantation itself takes only about an hour, in steps. First, they scan the brain to know where to place the threads. Then the skin is cut under local anesthesia, a hole is drilled in the skull, and the threads are inserted into the brain. The chip doesn't fall out because it matches the skull's shape and is made of biocompatible materials that later become essentially part of the skull, and it's fixed with special screws. You can see the screw holes in the video, then the skin is sewn shut. They aim for a result where even if you're bald, you run your hand over your head and feel no bump. Second, safety. In his 8.5-hour interview with Lex Fridman, Neuralink's co-founder and COO, talked about how the device is already at a good safety level. First, the FDA watches them extremely closely. They obviously don't want some random tech implanted into people's brains. So standards are very high, and they haven't seen immune reactions to the threads. Here's an image of brain tissue from an animal that had the chip for 7+ months. It has different cell types, and neurons are highlighted in brown. That little stripe is the threads themselves. The neurons lie right next to the thread, meaning trauma is minimal. Earlier chips before Neuralink damaged neurons around them. They didn't conform to the thread. The second image shows that these threads don't float around. They stay exactly where they were placed. And if someone asks how to remove or upgrade the chip, that's tied to safety too. Here's how. Either cut the threads and replace just the chip, closing the hole with a new chip or a plastic cap. Or, as they plan soon, make it not a single monolithic device, but two. The first part, threads, radio transmitter, chips, power source, under the dura mater. The second upper part went with more computing power and bigger battery, above it closing the skull. This way you can replace only the top part without cutting threads. In the first case, the cut threads won't migrate through the brain because scar tissue forms and holds them forever. The brain functions normally. In the second case, updating only the top part will be fast, less than half an hour. This has been the Matrix channel. Stay with me. A new interesting video comes out tomorrow.